All right, we have a particle in a state, particle in a state, and this cat is represented by that state. 2i minus 1, 4i. This is a column vector, or a vector or a column matrix, which is the basis, the orthonormal basis uh, of the cats u1, u2, u3. So if you do a broad cat with u1 and u1, which I have here, it's equal to 1. If they're not the same, it's equal to 0. That applies for u3, u2, and I have u3, u1 here. But what is in this? Well, this all this is a column vector. This is a basis vector. This is the basis. This is a matrix representation of the basis. This is the other basis. This is the basis. This is like ik, and ij, and z, or yeah, k. All right. If you just want to put these together and make a representation, matrix representation, you can add them together and you get this one column vector. But the basis can be separated into these three column vectors. So we have a state vector that represents a particle, and we're trying to do a measurement on it, and a measurement, or what we call a expectation value, we operate a variable on it, which could be momentum, could be position, could be mean value, or some other representation, which this is an operator. A is operator, which really A is operator, which is a matrix. It's a matrix. So I showed this down here. This is, you can see this is a 3 by 3 because you got 1, 2, 3, 3 dimensions. And the matrix representation really is the row and column indices here. So U11, this is a 1 coefficient in front of here. This is 1. U12, this is a negative 2i here. And U33 is 1 right here, 1 right here. And the rest of them are zeros because you can see that here. So you can see that with these brackets, they represent the indices or positions of the 3 by 3 matrix. But this is an operator. So in the same sense, you can take and multiply, you can operate this A onto this column vector. But we're not going to do it in this notation. Okay, so when we operate that, we do an operation, we got we got to calculate the bra, which we got to calculate, the bra. And when you take the bra and you do the bra, which is the representation is a row vector, you need to also take the complex conjugate if there's any complex values here. So this is what we did here. And you don't have to look at a row and a column. This is in the this quantum mechanics notation. So you have when you do that, you have a negative 2i. You have, of course, this doesn't change, it's a real number up here. And then you got a minus 4i, which up here is a 4i. And the bra is different. Okay, well, the next thing we need to do is we need to operate this operator, not this matrix, but this A here into this ket. When you do that, what you need to do is you need to, since these are constants, these constants can be brought out. So you operate them on each basis, A on each basis, A on U1, A on U2, and A on U3, the operator. So what is A is defined. So when you operate it on U1, you look at the representation of A, and you can see that this this bra is on this cat is U1, U1. And you do the same thing here. You operate it, which is the representation up here. You operate it on, we got a U2 on the U1. And up here you got U3, U3. You operate U3 on U1. And what do you get? You actually get, this is 1, this is 0, and this is 0, because they're orthonormal. When you got, like I said earlier before, U1, when U1 is 1, U2, U1 is 0, U3, U1 is 0. So don't get that mixed up with the real state vector, actual state vector. These are basis vectors, like unit vectors. So when these disappear to 0, and you're left with, when you operate on the U1 basis, you get U1. Now we do the same thing for U2, and I do the same thing. We got, you see the U1 and the U2, that makes that 0, and this U3 and U2 makes that 0. But U2 is 1. So the answer to the operation on the U2 basis is, operation A on U2 basis is a negative 2i U1. This so happened to just be, luckily get to U1, still U1, but here it's a negative 2i U1, now to U2. Now I didn't do the math on U3, but when you do the math on U3, you get U3. So in this case, you get something similar to U1. Now you put all that together. So you operated on all the orthonormal bases at the same time, bringing the constants out. So when you operate this operator, before you put the representation in there, you take the constants out. Some people may skip this step. It may be easier for you to do it. You may be, really math savvy to do it, but we don't want to make a mistake. And then, of course, I want to make this simple as possible, so you won't be bogged down in the complicated math, which is not really that complicated. Okay, so when you substitute all of, move the constants over, you already have A1 operating on U1 defined, A operating on U2 defined, we already calculated that, and a U3 operating on U3 defined. So when we do that, when we operate that on there, well, we got that defined as U1. On this, this is U1 also. So the basis U2 disappears. And then you have the operation of the A on U3, which is just U3. So when we operate on this particle state, we get, this is the result we get. So you have to do all that with the matrix representation, not thinking about integral, but just more or less discrete calculations. So what we got to do is we got to get the bra here on the other side, because we're trying to calculate the expectation value of A. I didn't say that before, I'm saying it now. That's what we're trying to calculate. We're doing a measurement. So in order to get that measurement, we got to calculate that, calculate the expectation value. Now, if you calculate operator, put operate on the state particle state, you could get maybe the group of values for that state. The expectation value is the expected value, the most probable value that you're going to get. So that's a little bit different. That now what I'm talking about is eigenvalues and eigenvectors. But that's not, that'll come in the future. That's not part of this. So the expectation value, we got the bra. So the bra is already defined. We calculated that, and that's here, right here. Negative 2i, U1, minus 1, U2, negative 4i, U3. That's what we have here. And we got all this representation here. So what you can do, you treat this just like just if you want to be careful not make a mistake. You treat this just like you're multiplying two polynomials together, and these are constants. So you put you can put u1, multiply u1 and u1 with u1, then multiply with u1, u3. Then you can write this all right, u2 operating on u1, u2 and u3. And multiply all that out. u3 operating on u1, u3 on u3. Now we already know that from here we said u2 and u1 is equal to 0, and u1 is equal to 0. Anything different, when the subscripts are not the same, they're 0. If they're the same, they're 1. So here, I didn't multiply all that out because I know all my zeros. I just focused on the ones that were the same. And the only ones that are the same with operators is u1, u1, and u3, u3. And what we have here, when we calculate that, this is a 2 times 4i squared. I squared is negative 1. We have 8 here. We have a negative 4i I squared times the negative 1 is 1. We got 16. And the expectation value for the operator is 24. So this is how you calculate using this Marquette notation, the expectation values. So I hope this helps. There's more to come. I'm trying to build upon what I did in other videos, and just want to make things simple because it's really not as complicated as we think it is. So this is Alpha Mad Scientist. Please subscribe to my channel, comment, give it a thumbs up, thumbs down, leave a comment. I hope this helps. There's more to come. I'm hoping to do a full system soon. This will include eigenvectors and eigenvalues.